All right, this video is going to be part 2 of solving some more trig, so let's go ahead and get started. I will say that these 3 problems down here are going to be treated differently. That's why they're a different color. And the reason is because there's a number in your B slot. So like most of these other ones don't have a number in the B slot. Well, if you do have a number there, you treat that problem differently. So I'll show you what to do. Let's go ahead and get started. I'm on number 1. If I see like cosine cubed equals cosine, the same function on opposite sides of the equation, generally the first thing that I'm going to do is I'm going to get it all to the same side. So that would look like this. I would move this cosine x. So now it equals 0. And so generally when you move stuff all to the same side, you're looking to either apply a rule or factor or something like that. So in this scenario, I would factor a GCF of cosine. So it would leave cosine squared minus 1 equals 0. Now you could probably treat this as a difference of squares and go even further, but I'm just going to leave it like that because this is basically factored. So once you have it basically factored, you can just set each factor equal to that 0 and solve each one. So on this one on the left, I'm looking for where cosine is 0. So that's going to be like pi over 2 or 3 pi over 2. And on this one, I would have to add 1 and then root it. And when you root it, you need to use a plus minus. So I'm also looking where cosine is either positive 1 or negative 1. So that would be at 0 or that would be at pi. So those 4 things would be my answer. Okay, let's move on to number 2. Now in number 2, let me write it out real quick. In number 2, I see that I have 2 different functions, a sine and a cosine. That's not good. You can't really solve this thing if you have 2 different functions like that. So what you need to do is look for a rule change. The only one that you could change here would be sine squared. You would have to change sine squared to be 1 minus cosine squared, like that. So this problem would turn into this. All right, so from here, I would distribute this 2. And then when you're looking at this right here, you're going to want to get everything to one side. But a really good rule of thumb is move whatever you need to move in order to make the thing with the square positive. So like if I moved everything this way, I would still have a negative cosine squared, which is not good for me. So I'm going to move everything to the right. So I'm going to add 2 cosine squared to both sides. I'm going to minus 2. So it's going to become 0 on this left side. And then on this right side, I get 2 cosine squared plus cosine. And then that plus 2 minus 2 cancel. So I'm here. Okay, well, the reason you wanted to do it like this is because now you can GCF a cosine out and be left with 2 cosine plus 1 equal to that 0. And now you can set each factor equal to 0 and solve each one. So the one on the left where cosine is 0, that's pi over 2 and 3 pi over 2. And the one on the right, you would subtract 1 and then divide by 2. So you'd end up with cosine x equals negative 1/2 And where that happens, you have to think, okay, well, what quadrants would that be in? It would be in quadrants 2 and 3. And your reference angle for this would be pi over 3. So you just give the location of pi over 3 where it would be in quadrant 2 and where it would be in quadrant 3. So in quadrant 2, it would be 2 pi over 3. And in quadrant 3, it would be 4 pi over 3. So these 4 things would be my answers. Just like that. That was kind of a tricky problem. Again, if I see 2 different functions, something's got to change. So I went after the one that I could change because it had the square. I could use the rule on it. All right, let's move on. The next one, number 3. I see, let me write it, but I see 3 functions right from the start. That is not a good thing for me. So let me show you what to do. I see 3 functions, but nothing's squared, and so I can't really use a rule change or anything as is. So I'm going to go after this tan. I'm going to do basically the only thing that I can do, which is to change tan to be sine over cosine. So you're going to end up with cosine over 1 plus sine squared over cosine. And now you need to be thinking common denominator. So I'm going to give this guy on the left a cosine over cosine. Then it's going to become cosine squared over cosine plus sine squared over cosine equal to that too. And now, since they have the same denominator, you can combine the numerators, and this is all going to equal 1. So really what you have here is you have 1 over cosine equals 2 after everything is all said and done like that. So from here, basically I look at this and I see fraction equal fraction. And when you have fraction equal fraction, that's when you can do your cross multiply. So you'll end up with 2 cosine x equals 1. Then you can go and solve this thing. So divide by 2, you get cosine x equals a half. So now is when you would think, okay, well that has to be in quadrants 1 and 4 for cosine to be positive. And my reference angle is pi over 3. So in quadrant 1, my answer is just pi over 3. And in quadrant 4, my answer would be 5 pi over 3. And that's how you would handle that problem. So I couldn't make a rule change right up from the start. So I went after the only thing I could, the tan, made it sine over cosine. Then I thought to myself, common denominator. Then I was able to solve this problem. Okay, let's look at another. Number 4 now. This one's real similar. I see 3 different functions. So I'm going to go after the tan because I can't make a rule change or anything. So it's going to look like this. Sine over cosine now times that sine x. You can call it over 1. Okay, so it's going to become sine squared over cosine minus 2. And I'm going to go ahead and get everything to one side. So I'm going to move that minus cosine x. Now it's going to become plus cosine x over 1 on this left side. And now it all equals to 0. All right, so once you're here, it can still look really confusing. So my advice to you is realize that you are trying to basically, well, that was weird. My screen blacked out for a second. You're trying to basically combine 3 different fractions. So in order to do that, you're going to have to give everything a common denominator. So this middle fraction needs cosine over cosine. This far right fraction needs cosine over cosine. So what this problem actually turns into is sine squared over cosine minus 2 cosine over cosine plus cosine squared over cosine. And that all equals 0. And so now you can combine all of these numerators, all this. And when you do this, you need to realize that there's cosine squared plus sine squared. That's 1. Then you have that minus 2 cosine. And it's all over cosine. And it equals to 0. Now from here, you need to realize that basically this is a fraction equal to a fraction. And you can cross multiply again. So what you're going to get is 1 minus 2 cosine equals 0. And then all you have to do is go solve this one. So you would subtract 1, divide by negative 2. That was the sound of all my papers hitting the floor. So you subtract 1, divide by negative 2, so this equals 1/2. And so once you're here, you can just be like, okay, quadrant 1 and 4. My reference angle is pi over 3. And so my answer for quadrant 1 would be pi over 3. My answer for quadrant 4 would be 5 pi over 3. I know that was tricky, but basically you wanted to change tan first to sines and cosines. That way, instead of 3 functions that you're dealing with, you're only dealing with 2. Then you need to realize you're trying to combine a bunch of fractions, so you need a common denominator. Once you have a common denominator, some rules will open up for you, and you'll be able to rewrite this and get it to a cross multiply finish. So that was a tricky one. I'm going to pick my papers up. We're going to pause and then keep going. Okay, number 5. So the main theme of solving all these so far has been to either factor or use rule changes, right? You don't always have to factor it. So here's what I mean. Look at number 5. When I look at number 5, it is very, very blatantly obvious that this is a difference of squares. So instead of trying to factor, I'm going to go the opposite way. I'm going to FOIL. So it's just going to make secant squared minus 1, because the outside inside of that FOIL cancels each other, just like a difference of squares. And then from here, there's a couple different ways that you could do it. You could add the 1 and then root it. Just don't forget plus minus. But I'm going to go a different route with it. I'm going to look at this and make a rule change and call that tan squared. Again, you do not have to solve it this way. There are other ways to solve this problem. So I would be here. Then I would root it. Don't forget plus minus if you root. So what you end up with is tan equals plus minus root 3. And if you see this as root 3 right here, you're going to freeze, because that's actually root 3 over 1. And you should write y over x next to it. So really, you're looking for a reference angle where the x numerator is 1 and the y numerator is root 3. So this reference angle is pi over 3. Oops. Pi over 3. And since you have that plus minus there, that means you're in all 4 quadrants, because you don't care if tan is positive or negative. So you're going to have 4 answers here. And then you just use that reference angle and say in quadrant 1 it would be pi over 3. In quadrant 2 it would be 2 pi over 3. Quadrant 3 it would be 4 pi over 3. In quadrant 4 it would be 5 pi over 3. And those would be my 4 answers. But again, you did not have to go about it this way. There are multiple ways to solve these. Okay, let's move on. Now we're at the weird ones. And again, these are weird because there's a number in the B slot. When that happens, your answer changes. So remember how we just had like an answer of pi over 3 here? I know there were more than that, but just think about this one answer. That's not your only answer. Pi over 3 is only one of your answers. If you were to do another loop, so 7 pi over 3, because I added 2 pi and got to 7 pi over 3, that's also an acceptable answer. What happens is there's an infinite number of answers. And so to counteract this, we generally say on the domain from 0 to 2 pi. And what this means is we don't care about the extra loops. We stop at 2 pi. So like this right here is bigger than 2 pi. It's 2 1/3 pi. So that answer we usually don't care about. But this right here is going to be very important for these three problems, and I'll show you why. Okay, cosine 2x equals a half. You still isolate cosine. And once cosine's isolated, you're able to inverse cosine, which I wasn't showing my work for earlier. Sorry about that. And you'll still think about what quadrants, so cosine positive, quadrant 1 and 4, and you'll still set up your quadrant 1 and quadrant 4 answers, and you'll still think about your reference angle, which for cosine to be a 1/2 is pi over 3. So all of that's still the same, and you would still go get those same answers. So for pi over 3, or quadrant 1, that's pi over 3. And quadrant 4, that's 5 pi over 3. But you need to realize that this inverse cosine only cancels cosine. It still leaves 2x equals that. Usually we would be done by then. It would just drop the x and you'd have your answer. But it still leaves 2x. And even more importantly, remember how I was saying this is just one of my answers? If I do a full loop and get back to this spot, I would have that same answer. You have to account for that by doing plus 2 pi n. Let me move this over and I'll explain what that means. 2 pi n, 2 pi is your loop, and n is your number of loops. This right here, plus 2 pi n, accounts for the infinite number of answers that you'll get. So on both of these problems, you have to assume that there would be that same answer in 1 more loop, or in 2 more loops, or in 3 more loops. And why this matters is because you're eventually going to have to divide by 2. And so what you're going to get is you're going to get x equals pi over 3 divided by 2 is pi over 6. And then this part, 2 pi n over 2 is pi n. And this one would be x equals 5 pi over 3 divided by 2 is 5 pi over 6. And then plus pi n, just like that. So like if your teacher's not looking for specific answers, this is technically correct. But they're probably looking for every single answer between 0 and 2 pi. So you have to list them all out. So what you need to realize is when you add pi in, you're really adding like 6 pi over 6 in. All right, so here's what it would look like. You have one answer of pi over 6. You then have to account for adding 6 pi over 6 to that answer. So getting 7 pi over 6. And you do this until you hit 2 pi. So like the next one would be 13 pi over 6. Well, that's greater than 2 pi, so it gets tossed. And these are my only two answers. And then on this one, you would have your answer of 5 pi over 6. And then you have to imagine adding one loop or 1 pi to that. So 6 pi over 6 added onto that would make 11 pi over 6. And you would do that again, 17 pi over 6, until it broke 2 pi. This one's bigger than 2 pi, so it gets tossed. So it's just these two answers. Okay, let me try to clarify all that in English. You generally have one answer because we restrict the domain. But you, on these ones in the with a number in the B slot, you can't assume that it's only that one answer. You have to account for it by putting plus 2 pi n after you inverse cosine or sine or whatever it is, because you're going to have to divide that 2 pi n by whatever number's in front of that x. And then you're going to have to add that amount to your answer. I know that was confusing. Just look at another one. If you can hear my dogs barking, sorry. Tan 3x equals 1. So if I was approaching this problem, the first thing I would do is I would probably inverse tan. And so the only place where, first of all, tan's positive is 1 and 3. And for tan to throw a 1 over 1, your y and your x have to be the same, which means pi over 4 is my reference angle because the x and the y are both root 2 over 2. So I know I have a quadrant 1 answer, and I know I have a quadrant 3 answer. And so basically, in quadrant 1, it would just be pi over 4. And in quadrant 3, it would be 5 pi over 4. But look at where these answers repeat. I guess, I don't know if I want to show you that way or the other way. Let's just stick with what we just learned. So one full loop, my answer would repeat. So that is plus a 2 pi n. My answer would be repeating. But this is not what x equals. This is what 3x equals. Meaning you're going to have to divide everything by 3. So you're going to get x equals pi over 12 plus 2/3 pi n. This one would be 5 pi over 12 plus 2/3 pi n. Like this. So you start with your answer of pi over 12. And then you need to realize that you're adding 2 pi over 3 until you break that barrier. So it would look like this. Pi over 12 plus 2 pi over 3 is the same thing as 8 pi over 12. So this is how much I'm actually adding each time. Meaning my next answer would be at 9 pi over 12, which reduces to be 3 pi over 4. This was 9 pi over 12. Okay, and then you would do it again because you still haven't broken that 2 pi barrier yet. So you're adding another 8 pi over 12. So that's going to be 17 pi over 12. Then you would do it again. You would add another 8 pi. But when you did it this next time, it would make 25 pi over 12, which is greater than 2 pi. So that one would get tossed. And these would be my 3 answers for this section only. Now I have to do the same thing with this section. So I have my original x equals 5 pi over 12. And I'm adding increments of 2 pi over 3, aka 8 pi over 12. So that's going to make 13 pi over 12. 21 pi over 12, which reduces to be 7 pi over 4. And then if I did it again, it would be 29 pi over 12, which is greater than 2 pi. So I would be done here. I hope that started to make a little bit of sense. Okay, last problem. Secant 4x equals 2. I don't like secant very much. So anytime I see secant, I change it to cosine. Not anytime, but a good amount of the time. And I flip this fraction on the right. So now it's 1/2. because I can see cosine being 1/2 much easier. So I would inverse cosine this now. And so that means for cosine to be positive, I'm in quadrants 1 and 4. So I've got a quadrant 1 answer, and I've got a quadrant 4 answer. And so remember, this inverse cosine only cancels cosine. It drops the 4x. And then you can think about reference angle. This one would be pi over 3. So 4x equals pi over 3 in quadrant 1. And in quadrant 4, that would be 5 pi over 3. And here's where you have to realize that it would, after one full loop, repeat that answer. So plus 2 pi n on both of these. So now, if you can hear baby crying, I'm sorry. We're almost there though, so I'm just going to keep going. Don't worry, her mother is with her. Okay, so from here, divide by 4. So you're going to get x equals pi over 12 plus 2 over 4 reduces to be 1/2. So this turns into pi over 2 n. And this one you would get 5 pi over 12 plus pi over 2n. Just like that. Okay, so your first one is pi over 12. You're then adding increments of pi over 2, which is actually 6 pi over 12. So that's the increment that I'm going to add to this first pi over 12 to get 7 pi over 12. Then I would get 13 pi over 12. Then I would get 19 pi over 12. And then if I did it one more time, I would get 25 pi over 12, which is greater than 2 pi. So I'm done there. That's just this first section. Now I do the same thing on this, the one on the right. So my first answer is 5 pi over 12. My next answer, I would be adding another 6 pi over 12, which is that pi over 2. So it's going to be 11 pi over 12, 17 pi over 12, and 23 pi over 12. If I did again, I would get 29 pi over 12, which is bigger than 2 pi. So I hope it started to come together a little bit at the end. They're not that bad. Just start with your 2 pi n, divide by whatever that B slot was, and that's the increment that you have to add over and over until you reach the threshold of 2 pi. So, hope this video helped.